of this lecture, today I will see first isomorphism theorem in ring theory. Today I will see by first isomorphism theorem Rx modulo ideal generated by x square plus 1. This is isomorphic to complex number. Also we will see, we all of us know the C01. C01 with a set of all continuous function f from 01 to r such that f is continuous, and this is C01 since this is ring with respect to the operation addition and multiplication, this is the continuous function. Then I will say C01 modulo f, the set f belongs to C01 such that f half equal to 0. This is isomorphic to whole real number. Today's goal of this lecture, today I will see these two parts, and I will prove this by first isomorphism theorem in ring theory. Okay, let's see first part. Rx modulo ideal generated by x square plus 1 is isomorphic to complex number. Notice here the curve phi is ideal generated by x square plus 1. So consider one function phi from Rx to complex number, and the function is look like phi fx equal to, since curve phi is ideal generated by x square plus 1, so the function would be such type phi of fx equal to f of I, because if you put here I, then this value would be I square plus 1, this value would be, after putting I, this value would be 0. Since this is the curve phi, so that means f of I equal to 0, and here obviously if you put in this equation I, then this would be 0. So for this curve phi, the function would be such type phi of fx equal to f of I. Now can you prove phi is a ring homomorphism? Just prove oneself at first, then see my video. At first pause the video and try to oneself. Is phi is a ring homomorphism? Phi of a plus g x equal to, obviously it would be a plus, by the defined function a plus gi, and obviously this means f of I plus g of I, and this is equal to phi of f of x plus phi of g of x. That means phi of a plus gx is equal to phi of f of x plus phi of g of x. Similarly, phi of f dot g x equal to f dot gi, and by the property of function this is equal to f of I times g of I, which is equal to phi of f of x times phi of g of x. So obviously this function satisfy the ring homeomorphism property. Now we need to prove phi is onto. For this, let consider a plus ib, arbitrary a plus ib belongs to complex number such that phi of this equal to a plus ib. And how look like the polynomial? The polynomial is look like ax plus b, because If you put I, then this would be a plus ib. The polynomial, the polynomial is look like a plus xb. If you put I, then this would be the value a plus ib. And this a plus xb is belongs to Rx. That implies phi is on 2. Then by first isomorphism theorem, we can tell Rx modulo ideal generated by x square plus 1 is isomorphic to complex number. And this is the curve phi. Then we need to show curve phi equal to ideal generated by x square plus 1. Ideal generated by x square plus 1 means x square plus 1 times some gx, where gx belongs to Rx. And what is the definition of curve phi? Curve phi equal to those fx in Rx such that phi fx equal to 0. And this is equal to those fx in Rx, phi of fx equal to 0 means f of I equal to 0. And this is nothing but, this is the those function whose root is I. And if we consider this type of factor, obviously its root would be I. But here notice we have to choose those function which belongs to Rx such that f of I equal to 0. This is not belongs to Rx. So in Rx the root is 1 is such type of function. So curve phi is ideal generated by x square plus 1. That means this is the curve phi. So by first isomorphism theorem we can tell Rx modulo x square plus 1 is isomorphic to complex number. I hope my all viewers have understood this process briefly. Okay. OL. C01. We all of us know this is the function from 01 to R. This is continuous function and this is ring, obviously with respect to addition and multiplication. And this is the commutative ring with identity. And C01 modulo f belongs to C01. If you put any real number between 0 and 1, if you put f of half equal to 0, then can you tell this is isomorphic to what? At first think and pause the video. Think yourself. Then see my video. This is actually would be isomorphic to real number. Here the kernel means ideal is f belongs to C01. We all of us know kernel is ideal such that f of half equal to 0. Here f of half equal to 0, which belongs to obviously C01. This is the ideal, means this is the kernel. At first proof, is I is an ideal? If I is an ideal, then I obviously belongs to kernel. Try to oneself. Obviously this would be the ideal in C01. And here the function is such type. Obviously this is ideal, because if you consider two functions g, f and g, such that f of half equal to 0 and g of half equal to 0. Then their subtraction, f minus g to the g, f minus g half would be obviously, this means f of half minus g of half. This is equal to 0 minus 0, which is equal to 0. That means f minus g belongs to ideal. Similarly, if lambda belongs to C01 such that lambda fx, by the property this would be lambda x times fx, and if you put lambda f half, then this would be lambda half times f of half, and since f of half equal to 0, so this value would be 0. Therefore, lambda f also belongs to the ideal I, where lambda be any scalar. So this is satisfy all properties of ideal. So I is an ideal. Also, phi is ring homomorphism. Also, phi is onto. For onto, consider a belongs to real number, any a from real number, such that we have to prove phi of f equal to a. For this, how look like the f here? Fx equal to 2ax, and this is belongs to C01 obviously. Then phi f equal to, since phi of f equal to f of half, phi of f equal to f of half, then this value would be 2 times a times half. That means this value would be a. Therefore, for choosing any arbitrary a, here I have got phi of f of x equal to a. That means phi is onto also. I will stop here. In my next video, I will discuss prime ideal. Just as a review. But at first I will highly recommend you, if you don't see my previous video of prime ideal, at first see those videos. Then next video would be more easy to understand.